Hello everyone, today's topic is about emotion stimuli map detection using unit segmentation. In computer vision, there are several types of visual recognition: classification, object detection, and segmentation. In classification, there is one class label for a visual image output, and if you do object detection, it requires localizing these objects within an image. And in segmentation, the class labels are mapped to each pixel for a visual image output. And there are two types of segmentation, which are semantic segmentation and instance segmentation. So let's look at an example of a classification. So given an image of this, this shape, and if you do classification, the machine is going to output one class label for this image. And if you do object detection, there is localization in addition to the output class label. So if you do semantic segmentation, um, given an image of shape, it's going to transform the image to um, the right image, which has three classes of road, shape, and grass, and each pixel in the image is mapped to one of these classes that correspond to that belong to the class. So uh, if you do instance segmentation, the um, the the objects within the same class are classified differently. So there are three shape, and each shape is classified differently as shape 1, shape 2, and shape 3. And there are five classes in total if you do instance segmentation. So how can we annotate the ground truth images for segmentation? From what I know, you can label each pixel using either tools of GIMP or Label Me. I haven't used it though. So here's an example image of a woman, and there are five classes, and these um, classes are classified for each pixel. So each pixel is annotated with one of these five classes. And fortunately, you don't have to annotate all the training images for their ground truth images. And there are public datasets that provide the original image and the masked image for segmentation, such as Pascal VOC or AID20K. There are many algorithms for segmentation: fully convolutional networks, UNet, pyramid scene parsing network, BeamLab, and ParseNet. In the following, we'll do emotion stimuli map ESM detection using UNet, which is one of the semantic segmentation algorithms. Before that, let's check about what ESM is. ESM, short for emotion stimuli map, describes pixel-wise contribution to evoke the emotions. Then why do we need to do pixel-wise annotation? The reason first is that because the emotional responses to images are not only affected by objects but also the emotional state and background of the viewer. For example, given an image of bungee jumping, it may bring excitedness to outdoors loving people. However, those who are afraid of heights will feel fear emotion. And the second reason is that the different regions within the same image evoke different emotions to viewers, as shown in the following images. So, images C, D, and E are cropped images from A corresponding to the rectangles of the yellow, green, and red in A, and the emotional response to image E is more similar to A than to either C or D. To represent the varying degree of influence from different regions of an image, the ESM, as in B, is used to show the higher influence with the brighter areas. Emotion ROI database provides the ground truth of the ESM, and they are generated based on the answers marked by the users in a user study. So here's an example of another reason why we do pixelized annotation for the evoking emotion. And the above figure shows the difference of ESM from salience and objectness detection. The ground truth ESM image is shown in B for the input image A, and the saliency in C focuses on the dark salient areas, whereas the objectness in D emphasizes the wizard flower in the image A. As can be seen, the ESM in B captures other emotion-related regions that are not conveyed by both saliency in C and objectness in D. So then how the emotion ROI database is collected? And the Amazon Mechanical Turk AMT is employed to collect responses from subjects for the 1980 images in emotion 6 dataset. The authors asked them to draw a rectangle enclosing the part of the image that most influences the evoked emotion, as in the leftmost image below. The other images show the corresponding ESM images for the original input image. Then, what is UNet? UNet has been first introduced for biomedical image processing. The architecture consists of two parts, which are the contracting path that extracts the context and the expanding path which performs precise localization. In contracting path, there are two 3x3 convolutions, each followed by a rectified linear unit. And 2x2 max splitting operation with stride 2 is followed by above two convolutions. And in expanding path, every step consists of an upsampling of the feature map, and each upsampling is followed by a 2x2 convolution, a concatenation with a correspondingly cropped feature map from the contracting path, and two 3x3 convolutions, each followed by a ReLU. And here's an example of unit architecture. And let's see in detail. So if an input image is given, let's assume that the original image is of size 572 by 572, and as I mentioned before, there are two convolutions followed by with three filter size 3. And because if you know the convolution operation, after one convolution with corner size or filter size 3, then it's gonna reduce to 5 from 572 by 572 to 570 by 570. And the number of filters, the number on the blue box represents the number of filters. So after convolution, so it reduced to 568 by 568. And 2x2 max splitting with the stride 2 is applied, so the size halves. So from 568 by 568, it is halved to 284 by 284, and then two convolutions followed by, and with 128 number of filters, and then again max splitting 2x2 with stride 2, so 280 divided by 2 is half, 140 by 140, and again above process is repeated, two convolutions max splitting, two convolutions max splitting, and up to here this is the end of the contracting path. And before you go into the expanding path, there is two convolutions followed by the upsampling. So after two convolutions, the output feature map of shape 28 by 28 is upsampled, so it becomes 54 by 54, which is two times the original output feature map. And then it is concatenated with a correspondingly cropped feature map from the contracting path, and the original output feature map is 64 by 64, and to concatenate it with a feature map of size 56 by 56, it is cropped to 56 by 56, and the number of channels is 1024, so it becomes 56 by 56 by 1024. And then two convolutions from 56 by 56 to 54 by 54 and 52 by 52, and upsample again, so 52 by 52 becomes 404, because if you multiply 2 to 52, then it becomes 104. So again, the output feature map from the contracting path of shape 136 by 136 is cropped to 104, and it is concatenated and two convolutions of sample, two convolutions, and this process is repeated until you get the output segmentation map. So how can we train the unit? The input images and their corresponding segmentation maps should be provided for training. And the original training data of UNEC contains 30 images. It took, according to the original paper, it took 10 hours on an NVIDIA Titan GPU for the original UNET paper, and directly adapting the original model to our problem is going to induce huge complexity, as we use 1782 images for training. Thus, we need a slight modification to UNET to train our ESM model. For the contracting path for the ESM model, the input image is resized to shape 128 by 128 by 1, and every convolution layer is followed by batch normalization and ReLU, and the padding is same, so that we don't have to crop the output feature map from the contracting path. And every second convolution layer is followed by max pooling with size 2, straight 2. This is the same as the original UNET architecture. And there are 5 such blocks, and every second convolution layer is saved for layer concatenation. So let's look at the expanding path. And the upsample followed by the two convolutional layers and concatenated with a corresponding cropped copy from the contracting path. So table 1 shows the architecture of the contracting paths of the ESM model, and whereas table 2 shows the architecture of the expanding path of the ESM model. And the output feature map from the block 4 is concatenated to the upsampled feature map named as U6. And as you see, the first subscript in the operation, both in contracting path and the expanding path, denotes the filter size, and the second one denotes the number of filters and the stride size for the contracting path and expanding path respectively. And C4 is concatenated to the upsampled feature map from the expanding path, and then the output feature map of the upsampled feature map is concatenated to C3, and C2 is concatenated to U8, and the C1 is concatenated to the output feature map from the transpose convolution. So let's look at the result from the trend ESM model. So as you can see, there are the first column represents the original image, and the second column represents the ground truth image, and The third column represents the predicted ESM, and as you can see for anger emotion, um, the predicted ESM is showing more weights to where the fire is seen. And for this fear image, it is the predicted ESM is showing more attentions on where the face is, where the scare face is shown. And here are some other images, and images of joy and images of joy predicting where there are people. um, um, for sadness, and for this image, where a person is cringing, the model is um, showing more attention where the person is cringing. And up to here, you've seen some of the up images of the trend ES model, and some images you may agree, but some images quite it's arguable that whether they represent the true emotion. Um, for this reason, these days I'm working on the formalizing the human emotions mathematically by analyzing the brain activities in human brains when they um, see a particular image. And however, it is worth noting that it somehow uh, shows us how to um, predict the pixel-wise contributions where the evoked emotions arise. And the UNEP model for this example is uploaded in GitHub. And up to here, this is the end of this video, and thanks for listening. Goodbye.